On December 7, 1941, a single 2026 Arleigh Burke Flight III destroyer materializes off Oahu to prevent the Japanese attack on Pearl Harbor. The warship carries the most advanced radar and missile architecture ever built. Its primary mission is simple: defend the United States Pacific Fleet and destroy the incoming strike group. It sounds like an easy win. It isn't. The central question is whether a modern warship can defeat 353 aircraft, or if geography and simple math will destroy it. At midnight, 7 hours before the first wave arrives, the destroyer powers up its combat system inside the harbor. The crew faces an immediate command choice. The obvious decision is to anchor near Battleship Row and act as a shield over Ford Island. From this position, the ship's weapons can cover the entire naval base. However, positioning a modern warship inside a closed harbor introduces a fatal constraint. The warship's primary defense relies on its Mark 41 vertical launch system. Standing still transforms a dynamic hunter into a stationary target. The Mark 41 system on a Flight III destroyer contains 96 missile cells. By quad-packing evolved Sea Sparrow missiles alongside standard missile 2s and 6s, the ship carries 128 anti-air interceptors. That is a massive loadout for modern air defense. But the Imperial Japanese Navy's Kido Butai is launching 353 strike aircraft. The tactical math is brutal. Even if every single missile hits with a perfect 100% success rate, 128 interceptors can only destroy 128 targets. That leaves 225 Japanese bombers fully operational in the sky. The missile magazine runs empty, while the enemy still has almost 2/3 of its strike force intact. Beyond the magazine limit, staying in the harbor creates a severe tactical vulnerability. Modern surface-to-air missiles require long-range radar tracking to calculate fire control solutions. Inside Pearl Harbor, two massive volcanic mountain ranges surround the anchorage. The Waianae Range rises 4,000 feet to the west. The Koolau Range reaches over 3,000 feet to the east. These physical barriers block radar waves traveling near the surface. Japanese pilots flying low through the Central Valley will be invisible until they cross the mountain ridgelines. At 06 a.m., the Japanese fleet begins launching its first wave 230 miles north of Oahu. On board the destroyer, the Aegis Baseline 10 combat system tracks 0 airborne targets over the northern horizon. The steel hull sits quietly in the calm harbor waters, yet the ship's tactical computer reaches a stark conclusion. The passive shield strategy is a delusion. If the ship remains anchored at its berth, the upcoming battle will not be a glorious defense. It will be a rapid war of attrition that the warship is guaranteed to lose. The combat system flags the physical blind spots and calculates the countdown to magazine exhaustion. To save the Pacific Fleet, the commander cannot wait inside the harbor for the sky to fill with bombers. The warship must break away from the pier and make a radical tactical decision before dawn breaks. Suppose the destroyer remains tied to Kilo Pier to test static harbor defense. At 07:49 a.m., Commander Mitsuo Fuchida's first wave arrives over northern Oahu. 183 aircraft split into precise strike formations. On paper, the destroyer's AN/SPY-6 radar should track these targets hundreds of miles away. In reality, basalt rock overrides high-tech electronics. The physical environment immediately breaks the Aegis combat system's outer defense layer. Radio waves from S-band AESA radars travel along strict lines of sight. They cannot bend over land masses or pass through mountain ranges. The 4,000-foot Waianae Range to the west and the Koolau Range to the east block the radar's low-altitude sweep. Japanese Nakajima B-5N2 Kate torpedo bombers dive into Oahu's Central Valley. They fly low between the volcanic ridgelines, completely hidden inside a giant electronic shadow. By the time the Aegis radar detects them, the bombers are already past the mountains. They are less than 10 miles from Battleship Row. System automation responds instantly. The Mark 41 vertical launch system opens, firing evolved Sea Sparrow missiles into the valley. Supersonic interceptors shred the lead Kate bombers before the pilots can react. Proximity fuses detonate, sending thousands of steel fragments through thin aluminum airframes. Modern surface-to-air technology works perfectly, yet tactical effectiveness is instantly neutralized by simple geometry and time. To engage targets emerging from behind mountain ridges, the combat system must launch multiple missiles in rapid succession. Within 4 minutes of continuous firing, all 128 anti-air interceptors leave their VLS cells. Plumes of white smoke billow over the deck, revealing 96 empty steel hatches. Over 50 Japanese aircraft collapse into the bay, but more than 100 bombers continue their attack runs unhindered. With the VLS cells empty, the destroyer relies on its final defensive perimeter, the Phalanx close-in weapon system. The automated radar-guided gun swivels toward a dive bomber screaming down over Ford Island. Its 6-barrel Gatling cannon fires armor-piercing tungsten rounds at 75 bullets per second. The incoming Aichi D3A Val disintegrates instantly into mid-air confetti. However, the Phalanx system possesses a severe hardware limitation. Its internal ammunition drum holds exactly 1,550 rounds. At maximum firing speed, 20 seconds of continuous stream firing completely empties the drum. As dozens of Japanese planes swarm from divergent angles, the Gatling gun spins dry. The static harbor defense collapses in less than 15 minutes. The destroyer's magazine counter reads 0. The point defense cannon is silent. Japanese bombers stream over the mountains, unbothered by further missile threats. They drop their armor-piercing bombs and Type 91 torpedoes into Battleship Row. The modern super warship stands totally disarmed amidst the burning wreckage of the Pacific Fleet. Remaining stationary inside the harbor proved to be a fatal tactical error. To change history, the commander must break away from Kilo Pier before the first shot is ever fired. At 02 a.m., 5 hours before the historical strike wave arrives, the commander completely abandons the passive harbor defense plan. The destroyer unmoors from Kilo Pier, navigates the narrow Pearl Harbor entrance channel, and accelerates into open ocean at 30 knots. By establishing an offshore picket station 30 nautical miles north of Oahu, the warship fundamentally alters the battlespace geometry. Moving out to sea eliminates the landward physical obstacles that previously disabled the Aegis combat system. In open water, high-frequency S-band emissions from the AN/SPY-6 radar propagate across an unobstructed 360-degree horizon. The basalt peaks of the Waianae and Kualau ranges no longer cast electronic radar shadows. By leaving the anchorage behind, the destroyer transforms from a cornered target into an active ocean predator. However, open ocean positioning introduces a new physical barrier, the Earth's natural curvature. A shipboard radar antenna, mounted 50 feet above sea level, cannot detect surface targets or low-altitude planes beyond 20 nautical miles due to the horizon boundary. To strike the Japanese fleet at extreme distances, the destroyer must extend its radar horizon using airborne sensor fusion. An MH-60R Seahawk helicopter launches from the aft flight deck and climbs to an altitude of 10,000 feet above the North Pacific. Elevating the radar platform to 10,000 feet dramatically pushes the line of sight beyond 120 nautical miles. The helicopter's onboard AN/APS-153 multimode radar sweeps the ocean surface, detecting radar cross-sections through night clouds and heavy sea spray. Through the HawkLink encrypted data link system, the Seahawk streams raw target tracking data directly into the destroyer's Aegis Baseline 10 combat computer in real time. The warship does not need to illuminate the target with its main mast radar. The airborne helicopter acts as an elevated remote eye, establishing a complete over-the-horizon targeting picture. This offshore maneuver creates immediate tactical friction across the North Pacific. Operating alone 30 miles off Oahu places the warship directly along the projected flight path of Kido Butai. High-power active radar sweeps from the AN/BY-6 system register as intense radio anomalies on Japanese radio direction-finding equipment. On the flag bridge of the aircraft carrier Akagi, intelligence officers detect unexplained electromagnetic interference originating from deep waters north of Hawaii. A long-range reconnaissance floatplane reports a solitary gray fast-attack warship moving at high speed without a traditional cruiser or destroyer screen. The discovery triggers immediate operational confusion among the Japanese staff. Imperial Navy doctrine dictates that if the fleet is discovered before launching its aircraft, the operation must be aborted to protect the capital carriers. Yet, because the unknown vessel is operating completely isolated without American air support or accompanying battleships, Admiral Nagumo hesitates to cancel the strike. Inside the destroyer's Combat Information Center, weapons officers prime 16 BGM-109 Tomahawk cruise missiles inside the forward vertical launch cells. The ship operates in an isolated tactical environment, completely detached from shore-based air defenses, while continuously burning high-purity aviation fuel to maintain helicopter operations. Every minute spent hovering at high altitude reduces the Seahawk's remaining flight time. If aviation fuel reserves run dry before missile launch, the ship's remote line of sight instantly collapses back to the physical sea horizon. Yet, for this critical tactical window, strategic control belongs entirely to the modern warship. At 10,000 feet, the Seahawk's radar beam cuts cleanly through 200 miles of ocean darkness. The tactical display flashes brightly, painting the precise coordinates of 6 massive aircraft carriers sitting completely exposed on the water. At 05:30 a.m., the destroyer executes a beyond visual range precision salvo using real-time targeting coordinates transmitted by the hovering Seahawk helicopter. 16 BGM-109 Tomahawk cruise missiles cold launch in rapid succession from the Mark 41 vertical launch system, igniting their turbofan engines and dropping to a sea-skimming altitude at 500 miles per hour. Operating over 200 nautical miles to the north, the Japanese fleet has zero awareness that an incoming strike is en route. Kido Butai possesses no radar early warning systems, no surface-to-air interceptors, and no automated point defense guns. The carrier task force is completely defenseless against modern standoff cruise missile warfare. The extreme lethality of this strike stems from a fundamental structural vulnerability in 1940s aircraft carrier design. In 1941, Imperial Japanese Navy main fleet carriers like Akagi and Kaga featured unarmored Douglas fir wooden flight decks built directly over open, unarmored hangar spaces. A modern Tomahawk carries a 1,000-pound WW-36 Bleep blast fragmentation warhead traveling at high subsonic speed. Upon impact, the heavy warhead easily punches through thin wooden planking without detonating on contact. The delayed fuse triggers the massive blast inside the enclosed hangar deck, where strike planes are actively being armed and fueled for the morning raid. A single Tomahawk impact does not merely tear a hole in the landing deck. It ignites volatile aviation fuel lines and detonates staged ordnance, initiating unstoppable secondary fires that destroy the ship from the inside out. The cruise missiles strike Kido Butai simultaneously across its wide carrier formation. Massive fireballs erupt from the wooden flight decks of Akagi, Kaga, Soryu, and Hiryu. Secondary explosions tear through internal hangar bays, detonating rows of Type 91 aerial torpedoes and 800-kilogram armor-piercing bombs. Burning aviation gasoline pours down into lower machinery rooms, causing catastrophic structural failure and rapid internal flooding. Within minutes, 4 of Japan's 6 main aircraft carriers burn uncontrollably, turned into floating infernos. The surviving carriers, Shokaku and Zuikaku, maneuver violently at 30 knots to avoid burning wreckage, while frantic radio signals flood Japanese tactical networks. This catastrophic standoff strike triggers an immediate doctrine response on the Japanese command bridge. Imperial Japanese Navy operational guidelines, recorded in official Monograph 97 battle protocols, dictate that Kido Butai's strategic survival depends entirely on absolute tactical surprise. The doctrine explicitly mandates that if the fleet is discovered or sustains preemptive attacks before launching its primary strike waves, Vice Admiral Nagumo must immediately abort the operation and retreat to preserve capital assets. Facing 4 sinking carriers destroyed by an unseen enemy, Nagumo adheres strictly to standard Imperial protocol. He orders emergency flag signals raised, commanding all surviving warships to cancel the Oahu strike and retreat northwest at maximum speed. The primary strategic objective is fully achieved before the sun rises over Hawaii. Not a single Japanese bomber ever reaches the airspace above Oahu. Battleship Row remains completely untouched in the quiet morning light, its fleet crews unaware that a historical disaster was intercepted 200 miles at sea. The destroyer's offensive strike magazine is now completely empty, with 16 Tomahawk VLS cells showing 0 remaining inventory. The airborne threat is eliminated, and Pearl Harbor is saved. Yet as dawn illuminates the Pacific and the combat crew calculates a historic tactical victory, the chief engineering officer enters the Combat Information Center with a devastating report about the warship's operational fuel supply. The tactical victory over Kido Butai is absolute, but the warship's long-term survival immediately collides with a fatal engineering reality. The destroyer's 4 General Electric LM2500 gas turbine engines require ultra-refined JP5 jet fuel or clean F-76 marine distillate to operate. In 1941, the United States Navy's entire Pacific supply infrastructure relies exclusively on heavy, unrefined Bunker C industrial oil. Pumping 1941 Bunker C fuel into a modern gas turbine would instantly clog the high-pressure fuel injectors, coat internal turbine blades with viscous carbon residue, and cause catastrophic engine seizure within minutes. Even if technicians attempted to filter the oil, modern high-precision fuel nozzles cannot tolerate heavy sulfur content or microscopic sediment. With 0 compatible fuel refineries existing anywhere on Earth in 1941, the ship's remaining JP5 fuel tanks represent a strict countdown timer, exactly 12 days of continuous operational endurance. When those 12 days expire, the warship's electrical generators shut down permanently. Without turbine power, the active liquid cooling loops fail, the AN/SPY-6 radar arrays go dark, and the Digital Combat Information Center freezes forever. Even if power could somehow be maintained through external shorelines, the ship's primary weapon system is permanently depleted. Mark 41. Vertical launch systems cannot be reloaded manually at sea or at standard 1941 naval piers. Rearming a single VLS cell requires specialized heavy-lift crane machinery, digital diagnostic interfaces, and solid propellant rocket boosters that will not be invented for another half-century. With all 96 VLS hatches empty, the world's most sophisticated surface combatant is permanently stripped of its missile arsenal. Beyond fuel and ammunition, the physical electronics face inevitable mechanical degradation. The Aegis Baseline 10 combat system and radar processing arrays depend on millions of microscopic silicon microprocessors, delicate fiber optic channels, and liquid-cooled solid-state transmitter modules. In 1941, global electrical engineering sits at the dawn of analog vacuum tubes, bulky glass components the size of human fingers. In an era where military radar operates on glass tubes and mechanical relays, silicon microelectronics represent an irreplaceable, non-renewable resource. If a single surface-mounted circuit board suffers a thermal spike or system short, no engineer or technician anywhere on the planet can diagnose, manufacture, or replace the component. A single blown microchip permanently degrades entire radar tracking channels or automated fire control systems without any possibility of restoration. The final tactical ledger reveals a profound contrast between immediate triumph and long-term obsolescence. On the morning of December 7, 1941, the counterfactual stress test delivers a decisive result. The Pacific Fleet battleships remain floating undamaged along Battleship Row. American military casualties stand at 0, and 4 of Imperial Japan's 6 frontline aircraft carriers lie at the bottom of the North Pacific. By shifting from a passive shield inside the harbor to an aggressive hunter 30 miles out at sea, a single modern destroyer successfully prevents the Pearl Harbor disaster and fundamentally resets the operational balance of World War II. Yet the modern warship paid for this historical rewrite with its own operational life. Unable to refuel, rearm, or replace a single printed circuit board, the 2026 super warship becomes a dead hull walking, a technological miracle stranded 85 years before its time. Within weeks, the ship will be stripped of its remaining fuel and rendered a silent floating museum piece. It proved that modern military technology can defeat an entire fleet in a single morning, but only when command masters the brutal mechanics of physics, terrain, and logistics.